Ladies and gentlemen, thank you for the invitation. I'm going to be talking about photophobia and visual stress in migraine. Migraine is a common disorder, and so is the photophobia with which it's associated. And in a review of symptoms of photophobia in an eye clinic, Buchanan and others listed photophobia and dry eye as the most frequent causes. Interestingly, they also mentioned that they used Fl41 tint, prescribed in almost half their patients, with 2/3 of those who used it reporting benefit. What is this Fl41? It's all over the web, and it's in fact a tint that I designed 30 years ago to reduce eye strain from fluorescent lighting. The idea was that by cutting out short wavelength light at the blue end of the spectrum, we could reduce some of the flicker from fluorescent lighting. That was because in those days, 30 years ago, the fluorescent lamps had a halophosphate coating that retained the light from 1/2 cycle of the electricity supply to the next. The lamps were controlled by a magnetic ballast that simply made a discharge twice with each cycle of the mains. And you can see that by cutting out short wavelength light here, one is reducing both the brightness and the color of the light, reducing the flicker that we showed was responsible for headaches. But that was 30 years ago. And since then, the technology has moved on. Fluorescent lamps have different coatings, and nowadays they're controlled with electronic ballast for the most part that operates the lamps at 20 kilohertz, where the flicker doesn't matter. These Fl41 tints were shown to be of benefit in reducing childhood migraine, but that was, again, a long time ago, 1991. And I think that was because most of the children were in classrooms lit with halophosphate fluorescent lighting. Many of them still are. And I don't know whether the Fl41 tint would be of any use in other contexts, but it's still being prescribed, as you can see. And I think the reason is that the IPRGCs have been implicated in photophobia. You can see the spectral sensitivity of the IPRGCs, the intrinsically photosensitive retinal ganglion cells, shown in green here. And you can see that the Fl41 tint gets rid of most of the light that they would absorb. Now, the idea that the IPRGCs were involved in photophobia was first put forward, I think, by Noceder and Burstein in this paper, which has been widely cited in many reviews of photophobia in the subsequent decade. The idea is that the intrinsically photosensitive retinal ganglion cells are responsible for photophobia. But since they wrote their paper, Noceder and Burstein have changed their position. They now think that abnormal processing of light by both cone and rod-mediated image forming and melanopsin-mediated non-image forming pathways are involved. And that's because they've done studies showing that green light reduces photophobia during a headache, and studies looking at the ERG, the electroretinogram, and showing rod-type abnormalities. So the picture is a little bit confused. Sensitivity to bright light might involve the IPRGCs, but it's difficult to see how the other sensitivities that patients with migraine have, to flickering light, to patterns, to color contrast, to lighting chromaticity, how they can be explained in terms of the IPRGCs. I don't think they can. but they can be explained, I think, in terms of the cortical hyperexcitability with which migraine is associated. I'm going to go through each of these in turn and say a little bit about the sensitivities. Flickering light, that is the flicker you can see, flicker below flicker fusion, where the flicker is very obvious, is uncomfortable, and large steady-state visually evoked potentials have been recorded in migraine in response to flicker. But above flicker fusion, where the flicker can't be seen, where it reaches the eye, but the eye is not aware of the flicker, that can still induce headaches, as we showed in 1989. And that may be because of the pericardic pattern. Let me explain what I mean. We are always moving our eyes. 2 to 3 times a second we make a saccade, a rapid eye movement. And when we do, the eyes move very rapidly. And during a large eye movement, a large saccade, the eyes can move at velocities of up to 700 degrees a second. And that's why you can see a repetitive pattern from intermittent lighting. The repetitive pattern is called the phantom array, which is a silly name because it's nothing to do with phantoms. And yet you can see it in the LEDs of the backlights of cars sometimes. The LED is intermittently illuminated, at least it was in some of the early designs, and as a result, in order to cool the lamps, and as a result you could see this irritating phantom array every time you moved your eyes. Now some people can see this phantom array, this pericardic pattern, with flicker that has a frequency as high as 11,000 flashes a second. And these people tend to suffer visual stress in everyday life. The threshold frequency is shown here on the x-axis, and each point here is an observer. And on the y-axis, we have the visual discomfort score from Conlon. I'll show you that in a minute, but you can see there's a correlation between the highest frequency at which they could just see the flicker and as a pattern, not as flicker, of course, as a pattern, and the visual discomfort score that they have. This is Conlon's questionnaire. Some of the questions are, do the letters on a page of clear text ever go blurry when you're reading? Questions of that kind. They're not related to flicker sensitivity as such. Now, Intra-Psychotic perception, this perception during the flight of the eye, during a rapid eye movement, has recently been shown to be used by the brain. We use the smeared image that we see during a saccade. We're not aware of it, but during a saccade, you get a blurred smear of the image, and that is used to guide, to link object locations across saccades. So the brain is using this information in the smear to indicate where the next object will be. Now, that information is clearly disrupted by any flicker because the flicker is producing this periodic pattern as a result of the intermittent illumination of the scene. So it's possible that that's interfering with the control of object locations in space. Now I want to talk about patterns, and I'm going to show you a nasty pattern, but before I do, I want to alert you to the fact that some of you, those of you who have epilepsy or migraine, should avert your gaze because this pattern can provoke seizures and it can provoke migraine. I'll only show it for 2 seconds in the next slide, and then I'll take it away. So avert your gaze now, if you wish. Are you ready? There's the pattern. It's thoroughly obnoxious. It induces glare, discomfort, and illusions of movement and shape and color. And these illusions that you see in the pattern are related to the headaches you have. So if you have a lot of illusions, then you have more headaches. If you look at the pattern on a daily basis, you can tell when your headaches are coming because you see more illusions. And if you have illusions more on one side of the pattern than the other, then you're likely to have a headache on one side of the head. These illusions are due to cortical hyperexcitability, as far as I'm aware. The visual stimuli that are uncomfortable to look at are similar to those that trigger seizures in patients with photosensitive epilepsy. They have the same spatial frequency, the same temporal frequency, and these are where the sensory thresholds are lowest. There's the same effect of brightness contrast, the same effect of color contrast, and both of these are determined by the cortical magnification. And all the above characteristics determine the strength of the visual stimulus. And both headaches and seizures are triggered by strong visual stimuli acting on a hyperexcitable cortex. In the case of epilepsy, things are slightly different because epilepsy also requires that the stimulus synchronizes the neuronal activity, whereas that isn't the case in migraine. So a drifting grating, such as this, will not trigger seizures, strangely, but it is migrainogenic. And that's incidentally because the receptive fields of cells overlap one another, and the contours move into and out of the overlapping receptive fields, creating a strong excitation, but not a rhythmic one. Now, there are many patterns of this kind in the modern urban environment. You can see a few of the patterns here, the stripes and so on. And we can measure these stripes using the Fourier Transform. This is the two-dimensional Fourier Transform. And in most natural images from nature, that Fourier Transform has a very particular shape. The amplitude falls off with the reciprocal of the spatial frequency. So if we make a cone in this two-dimensional Fourier Transform and fit the cone, the green surface here, we fit that to the Fourier Transform and measure the residuals. The residuals are an indicator of how natural that image is, how close to nature that image is. And in general, you find that if there are a lot of residuals and the image is a long way from nature, statistically speaking, it's uncomfortable to look at. In general, we can explain about a quarter of the variance in people's judgments of discomfort simply on the basis of the residuals. But not only discomfort, images that have high residuals that are unnatural in this statistical sense produce a larger hemodynamic response. The grey rectangle is where the images were presented, and the upper curve is for images that had residuals above the median, and the lower curve residuals below the median. So this statistical treatment of images is enough to predict the brain's response to the image and the discomfort that it evokes. Similarly, in color contrast, actually, I'm going to show you a colored pattern now. Again, I'll do it very briefly, but I'll show it just for 2 seconds, and then another pattern. And I want you to determine which you think is most uncomfortable. Here's the first one, which is fairly uncomfortable. And here's the next one, which if you look at it for a while is really uncomfortable. We find that in general, the discomfort is proportional to the separation of the component colors in this CIE diagram. In other words, the color contrast. The more contrasted the color, then the worse the pattern. It's not determined by the particular colors, simply by their separation in this diagram. So on the lower left here, we have a relatively comfortable pattern that gets worse as the component colors are separated further in the diagram. And in general, not just the discomfort, but also the electrical response. The EEG alpha power is attenuated more with the uncomfortable patterns. And again, you get a larger hemodynamic response in proportion to the separation in the color diagram. So once again, images that are uncomfortable are evoking a strong brain response. Now I want to consider lighting chromaticity. In the natural world, we're exposed to light that comes from the sun. The sun is a black body radiator. That is to say, if you take a black body and heat it up, it glows red, then it glows yellow, orange, and then yellow, and then white hot, and then blue. In other words, the color follows this Planckian locus. And in general, the sun lies on this locus, and most artificial light lies close to the locus. We wanted to see what would happen if we asked people who had migraine and people who didn't to select a color they found comfortable for reading. Would they choose a color close to this locus, one that they've experienced before, that they're used to, or would they choose another color? And these are the results. Oh, before I show you the results, this is the instrument we use to create the color. The subject looked at a page of text illuminated by light from a fluorescent lamp. The light from the lamp passed through a cylinder on which were mounted colored filters, 7 colored filters. And as the cylinder rotated, changing the colored filters and changing the hue, but the cylinder could also slide along its axle to expose more of the gray filter and change the saturation. So we had, without changing the brightness, we could change the hue and the saturation, the two intuitive parameters that we wanted to explore. We used, before I tell you that, this is the modern system, which is a similar process, but with LEDs and computer controlled. And there's a similar spectral power distribution in the colorimeter to that from lenses under typical lighting. The procedure we used consisted of increasing the saturation and then decreasing it at a particular hue, then changing the hue and increasing the saturation and decreasing it again. So we could shortlist the good hues, and then at one of the good hues that the subject liked, we could allow adaptation to the color and then iteratively change the hue and saturation and the hue and the saturation until they'd honed in on a comfortable color, allowing for adaptation to that color. The results we got were surprising. First of all, the controls on the left pictures here. These are 2 studies, the first by Aldrich and the second by Fourier, and they're different participants, as you can see, and different examiners, but the same results. The controls are shown by the dots. Each dot is an observer, and most of them lie clustered on the Planckian locus, as you can see. Contrast them with the participants who had migraine with aura, and you can see they chose colors well away from the Planckian locus. A very different distribution indeed. And no one color suited everybody. Everybody's choosing a different color, as you can see. But the characteristic in migraine with aura is that all the choices lie well away from the Planckian locus. That means, if you think about it, that the people with migraine with aura are choosing light that they never normally experience. They would normally experience light close to the Planckian locus, and they're choosing a very unnatural color, which is surprising because in other contexts, images from nature are comfortable. Here, however, lighting from nature is uncomfortable. We showed that this color made a difference by giving the patients a word search task. They did this using lenses that simulated the color they'd just chosen in the colorimeter. They had to search for the word at the top of this matrix, and if you can't find it, it's here. And then they had to touch the first letter of the word, and the computer recorded how long they took to do it. And they were very considerably faster with the light of the color they'd chosen. This is the migraine with aura, migraine with aura, and you can see that there's a 40% increase in visual search speed. The bars indicate the standard deviation, not the standard error. There's no effect for controls or migraine without aura. And this effect doesn't seem to be due to the energy captured by the IPRGCs. In the lower left, we have a diagram where the size of the points is proportional to the energy captured by the IPRGCs, the melanopic energy. And you can see that the size of the points in this diagram bears no relationship to the distribution of the color choices made by the patients who had migraine with aura. So in this context, at any rate, it doesn't look as though the IPRGCs are responsible for their choices. Perhaps the choices can be explained by cortical hyperexcitability, because colored glasses have been used in the treatment of photosensitive epilepsy for 50 years, with a little series of my own as well. Sometimes they're effective at eliminating seizures, not always. But color filters are also shown to be effective in not only a migraine, but autism, Tourette's, stroke, head injury, and multiple sclerosis. And there are papers on all these conditions. And all of these conditions, of course, are comorbid with epilepsy. Interestingly, the color filters don't seem to have much effect in retinal disease, except those standard filters that sometimes use. The precision filters don't seem to have a role. So it looks as though cortical excitability might play a role in explaining these results. So we can now use this simple reading speed test to diagnose patients who have visual stress. The patient simply asked to read aloud as fast as he can under light of a particular color and under white light, and we compare the reading speed. This test has high precision and high reliability, and an increase in more than 15 words per minute is well above the intra-subject variability. So we can now diagnose visual stress, and we can tell when color is likely to be of clinical benefit. So to summarize then, photophobia in migraine is not just sensitivity to bright light, but to flicker, patterns, and color. And this aversion is most parsimoniously explained, in my view, by cortical hyperexcitability. And if the IPRGCs do have a role in sensitivity to glare, it may be exacerbated, as it were, by cortical hyperexcitability. Thank you.